This video is about graphs of functions. Of course, our context here is intermediate algebra, and we have recently introduced and defined what a function is formally. So now we're going to extend and apply it to some graphs here. We'll begin with this major note, and that is a graph represents a function, there's our keyword function, if any vertical line intersects it at most once. This is also known as the vertical line test. You'll probably see that phrase showing up here and there, and this is how we can test or check just by looking at a graph whether it represents a function or not. Remember, not every relation is a function, as we saw when introducing functions. So let's go ahead and try to apply this vertical line test definition of functions to a few examples. Now, the first example is on a coordinate plane. So we have our x and y coordinate plane, you could think of them that way. And we have what would be also maybe seen as a typical parabola. So it's an upward opening parabola with a vertex down at the origin. And we want to know, is that a function? Well, to test it, we can use these vertical line tests, which basically amounts to just kind of sketching some vertical lines, segments through the graph, just to determine, is there anywhere in this graph, either visible here or maybe by extension that we can't even see, but following where the arrows are going, that where this graph might cross, or any vertical line might cross the graph more than once. And the answer, as can be seen in this picture, is no. Every vertical lines we can kind of just sketch on here would cross this parabola looking thing, this curve, only once, which means, yes, this graph represents a function. That's how we could answer that. Let's take a look at another example. The next one uses the graph of a line that's just kind of slanted from top left down to bottom right. And to run the vertical line test and determine if this represents a function, we could again just draw some vertical line segments, just kind of scattered throughout this slanted line, and you'll find, okay, obviously they're only going to cross it once, and even if you extend to the left or right off of what you can see, the same would be true, which means yes, that represents a function given that test. Our third example is you could maybe describe it as a sideways facing parabola. So it opens upward to the right, and then it kind of curves down with a vertex, somewhere to the left of the y-axis, but then keeps bending down and then kind of back toward the right, ending with an arrow pointing down to the right. So it's a parabola that's kind of opening to the right side. And same question here, does this represent a function? Well, it only takes one vertical line to demonstrate that, no, you would hit this graph more than once with any such vertical line as we've drawn. It only takes one example to show it's not a function, so we would have to say, no, that's not a function based on that vertical line test. Now, we also want to be able to understand some other basic characteristics of graphs and functions. So we're going to explore one such example here where we want to graph f of x equals x squared. Okay, so that's our function, f of x equals x squared, on a calculator. So this is in function notation. And by the way, f of x is synonymous with y. So this is kind of like the old y equals x squared, if you've ever seen that graphed before. Same thing, and now we're using function notation, so we say f of x. But this is a typical parabola. That's what x squared will produce. Now, I want to explore what happens when we take that graph, but then also pair it with another one that's slightly different. So the next one we want to compare is f of x equals x squared, but then a plus 2 kind of added on the end of this second example. Let's go ahead and take out our graphing calculator here. So I have an example here as in a TI-84 Plus. That's my recommended and used one for a course like this. We're going to go ahead and open that up, turn it on, get back just to the clear blank screen. And first of all, understand how to type in a function like this to the calculator to see a graph. We'll begin by hitting the y equals button in the top left corner of our calculator. When we hit that, it should give us a screen where we have y1, y2, y3, y4, and so on, but they're all blank. So we want to go ahead and just utilize the first one for now, y1 equals. After the equal sign where our cursor is flashing, we want to try to type in here x squared. That's our basic function. So we're going to hit the key that has the letter x on it. Of course, it has other letters on it too. It says x, comma, t, comma, and then a couple other things, theta and n. We want to hit that key, which will show or put an x in our window. So we have y1 equals x, but we want x squared, so we hit the up arrow caret to give us an exponent, and then we want to type in a 2 for that exponent. Now, that means we have y1 equals x squared. That's typed in as our first equation. To be able to view the graph for it, there's a couple ways. You can just hit the graph key, the top right button, but that's going to utilize whatever window was previously set and used in this calculator. So I prefer to kind of refresh it every time we're graphing it. If you hit the zoom key, this is in the middle at the top row of buttons underneath the window here, zoom, and then usually either zoom 4 or zoom 6 will give us what we need. So zoom 4 is zoomed in a little bit, and zoom 6 is zoomed out a little bit. I'm going to pick on zoom 6 for now. I'll just hit the number 6, and then it goes right to the graph and shows us the graph of this parabola. Of course, it's going through the origin where the vertex is. It's opening upward, as we might be expecting based on what you've perhaps observed from this graph in the past. But that's how we can look at the graph of a function like this. Now, you can also view the table of values for a function in the TI-84 Plus calculator like this simply by hitting the second button and then the graph button, and this will take you directly to a table where you have a column of x's and then a column of corresponding y values. Notice it says y1. So those values are all just the x values squared that are across from them. So that's a good feature to know how to access as well on the calculator. Let's go back to the graph by just hitting the graph. Remember, if you hit the graph key in the top right, it'll use whatever window was previously set. So if I just hit this, it'll take us back to what we used as the zoom 6 window, which is a standard, square, rectangular kind of window, where we just see our graph. Now, in this example, we wanted to explore what happens when we use x squared plus 2 as our second function in comparison. So we're going to leave this graph where it is, but now go back to the y equals by hitting that y equals button in the top left. Now let's go down to y2 equals. And in this one, we want to type now, this time, x squared. So again, x, and then you can just hit the x squared key. It'll put automatically a squared in there. But now I want to put a plus 2 at the end of this function, like we wrote, to compare what that would do to the graph of this function. Now let's go ahead and just hit the graph key since we want to utilize the same window. It'll add this second graph to our picture. Notice it's a very similar looking parabola, except this time it seems like it's shifted maybe up a couple units. Well, it turns out that that corresponds directly to the way that this was written out as x squared plus 2. Remember, we said we're just adding 2 on at the end of this function's definition. And so it turns out that doing that, putting a plus 2 there at the end, simply shifts the graph up 2 units. Now, there's a lot more where that came from, and there's a lot more we can do with functions like that. For now, we're just kind of observing that in the context of understanding the graphs of functions. Okay, we'll do a lot more with the broader topic known as transformations, of which this is only one type. But for now, we just wanted to take a look at how to put in a function to the calculator and what that simple adjustment would do to it. Let's now go on to some other examples where we want to start with some graphs already given, and we want to use interval notation to find the domain and the range of these examples of graphs given. Now, we have 4 of them drawn. I'm going to describe them as we go, in case you need to rely on a verbal description instead of a visual one. So our first example starts with a circle, so this would be like a missing point, a circle surrounding what would be the point -5, 3 on the xy coordinate plane. There's a circle there. And then from that circle connected, kind of veering downward and then toward the right, kind of curving down to the right, we hit eventually the solid point at 0, -4. Okay, so that's the description of this graph. Now we want to be able to describe from it the domain and the range, and we want to do so using interval notation. Now remember, as we've defined in functions, the domain typically pertains to the x values being used. Now, that can be a little tricky at first when you're looking at a graph that is two-dimensional, but you're only trying to think about one dimension at a time. So when I say domain, I'm only talking about the x values. That's the horizontal values only. So the question is, which horizontal values am I using in this graph? Well, clearly, according to this, I go no further left than -5. Now, because there's an open circle at the left boundary of this graph, my domain should have a curved parenthesis to actually exclude that boundary value of -5. So I want to put -5 as my leftmost boundary, but a parenthesis surrounding it because I'm not actually using it, denoted by the open circle in the picture. And then my rightmost boundary, if I look at this graph, it goes no further than, now be careful here, remember we're only thinking of horizontal values. This solid point we have plotted, really it's the point 0, -4, but the x-coordinate of that point is 0, which means I go no further right than that. So I'm going to use 0 as my right boundary, and since we actually hit it with a solid dot, I'm going to use a square bracket for the boundary symbol. So our domain is left parenthesis -5, 0, right bracket. That's interval notation for the domain. Now for the range, we're going to do this exact same kind of thing, except now we have to think only of vertical values, up and down. Remember, range is y values. Now what can be tricky about this is that we still have to write the range in a left to right increasing order in interval notation, even though we're going to be thinking low to high instead of left to right. So think the lowest value our graph uses is way down at the bottom where our solid point is. That's the value -4, as we've already discussed. But since we have a solid point there, we're going to use a square bracket for that left boundary. So we have left bracket -4, comma, that's the lowest value. Now we want to find the highest value. Well, remember, our graph goes as high as this open circle, which is at the coordinate -5, 3. The open circle means we don't actually ever get to that edge, but we know that the vertical value of 3 is the boundary there. We have to put a parenthesis as the boundary symbol since we don't actually get there with the open circle. But that now is the domain and range using interval notation for that particular graph. Let's try a second example. This one is the graph with a point starting at -3, 0, and then a graph which kind of curves and launches upward to the right as it curves, and then ending up with an arrow pointing up to the right. So it's kind of launching, maybe curving to the right like a rocket would launch from Earth, getting into orbit or something. And that's just the visual of this graph. Now, the domain, of course, is only the x values. Of course, it goes no further left than -3, so we'll put -3. Since there's a solid dot there, we use a bracket. Then we'll say comma to the right. Now notice there's an arrow on the right side of this graph, meaning it just keeps going. We represent that with the infinity for infinity, the symbol for infinity, which is like a sideways 8. And it's positive infinity since it's going to the right on the x values. And we always put a parenthesis by infinity no matter which side it's on. So we have a bracket at -3, comma, infinity with a parenthesis to the right. Now, the range for this particular graph, again, that's low to high. The lowest value would be a solid dot at 0. So we put a bracket on 0 on the left side. The highest value, now notice it's curving to the right, this graph is, but it also is kind of veering upward. And if we let that happen forever, it will continue to increase as it goes. So we'll also put infinity for the highest y value. Of course, that's not really a highest value. That just means it keeps going. Close it with a parenthesis since the arrow is there, meaning it doesn't ever end. It just keeps going. So that's our domain and range for the second graph. Let's try two more examples. The third one is a graph where you have kind of like almost like a lounge chair shape where starting from the origin to the left, you have just a flat horizontal line on the x-axis with an arrow going to the left. But then from the origin going to the right, it's going to kind of be just a slanted line going upward to the right, a diagonal line. So in that way, we could define the domain. Remember, domain is x values. That would be really anything because it goes forever to the left, forever to the right, as given by the arrows on each end, which means our domain is going to be negative infinity to positive infinity. That's another way to say all real numbers. Now the range for this graph, which we'll put here next, will be, remember, it goes no lower than this horizontal flat line part of it on the x-axis that's going to the left. So since it goes no lower than that, we have to use 0 as the y value boundary. That's the lowest it goes. But since it actually kind of rides right on 0 on the x-axis, we can say it actually hits it, which means we put a bracket on 0, comma. Now since it goes diagonally upward to the right with an arrow, we say it goes up to infinity forever as the right boundary of our range. Moving on to our last example, this graph is a little odd. It looks like just 4 distinct points plotted, and that's exactly what it is. There's one at -8, 3, -5, 3, -2, 3, and 5, 3. Now, this kind of graph is perhaps less usual when discussing algebraic functions, but it is a function nonetheless. The domain and range, though, they're only going to have a finite number of values. There's only 4 points here, which means we can probably better express them using set notation. What I mean is, for the domain, there are only 4 distinct x values being used, and that's the x value of each point. So we could just list those values in a set, which is these curly braces. The first x value is the -8. I'll just go left to right, though the order doesn't really matter in set notations. We have -8, comma, -5, and then comma, -2, comma, 5. That's just, again, going left to right. And then our range could be described similarly in set notation. But notice, range is y values, and all 4 of these points have the same y value. They're all at a vertical level of 3. And so the range is actually just one number. It's just the number 3. That's the only y coordinate used for any point in this graph. So we have domain and range here specified in set notation simply because it's more convenient with a finite small number of values to list as we have done for it.